So here's a kind of a neat example where we can learn a little bit of biology and also use what we learned about Bernoulli trials in the last segment. I have to remind you that each of us has a genome that's made up of DNA, and it turns out that there are little spots in the genome that are a little bit unstable, so that in a parent you might have a repetitive sequence CA, and in a child, or maybe grandchild or great-grandchild, this repeat may have been extended by a mutation to have a different length, CA, as you see here. And this can be used to figure out how ancestry works, because most of the time, from parent to child, the number of repeats is carried on exactly, but some of the time it changes. And as a rough number, there are about 0.5%. There's about 0.5% chance per generation, per location like this, of the number changing by usually 1. And these things are called short tandem repeats. Now, short tandem repeats change both from father to son or daughter and from mother to son or daughter. But if we want to get paternal ancestry, that's fathers, 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 we can just look at the Y chromosome, because a Y chromosome is passed on only from father to son. Females don't have a Y chromosome. So here's a map of the Y chromosome. Chromosomes have two arms, the P arm and the Q arm, and then here's a scale along the chromosome. And someone has gone in and found locations of these short tandem repeats. YSTR, Y short tandem repeat, positions along the Y chromosome, and given them names. And there's no shortage of them. If you want to have a uniform DNA identity system, for example, like the one the FBI uses, you just agree on a standard set of these markers to use. This map comes from a company called Family Tree DNA, and they're actually in the business of measuring your DNA to figure out who your ancestors or relatives are. You spit in a little vial and send it in, and they send you back a nice certificate like this one that seems to belong to someone named Larry C. Visner. I hope he gave permission for them to show his certificate on their website. This seems a little bit opportunistic or of the moment, because in just a few years you won't have to pay for a certificate like this unless you want a fancy looking one, because your whole genome will be sequenced by your health plan and will be some information that you basically own. Well, how do we get a statistics problem from this? We have to go to Margaret, my ex-wife. She's a great ex-wife, and she really got interested in the Towne family. The Towne family is an old New England family, and I have to tell you that Margaret is neither a biologist nor a Towne. This was just something that she got interested in. And the Towne family trace their ancestry to William Towne up here, who was born in England in 1599, and he, along with his 4 sons, 3 of whom we know about, emigrated to New England, to Massachusetts, in the early 1600s, and they have ancestors all the way down to the present day. The 3 original sons that we know about are named Edmund, Jacob, and Joseph. And if we look, for example, at Jacob's descendants, they go down here, through this line. Here are 2 brothers. We come down here. And eventually, at the bottom of all the branches of this tree, we reach towns who are identified only by number, because they are living towns, and the Towne Family Association wants to preserve their privacy. So starting at this side, we have T2 Towne, T11 Towne, and so on. They're not in any particular order, all the way over to T13 Towne. And what's interesting about these living towns is that they belong to the Towne Family Association, and the Towne Family Association sent all of the DNA in to Family Tree to be measured. And let's see what the data actually looks like. So ignore this yellow row for a minute. The other rows are the living towns that we just mentioned. Here are the descendants of Jacob. Those are these ones in this middle branch down here. Here are the ones of Joseph, and here are the ones of Edmund. Now what's plotted across in the columns are the 37 loci, positions along the genome, that Family Tree Incorporated decided to use in their standard test. You actually buy a certain number of loci from them, and 37 is the Grand Economy package or something. I'm making that up. But I want to point out that T13 here didn't buy all 37 loci. He bought only the 12 locus package. And therefore we have this data. So each box is for a certain locus and a certain member of the Towne family, how many repeats of one of those repeating DNAs there are at that point. Now, if we, for example, just focus on these towns, the descendants of Jacob, you can see that almost always they exactly agree. Here's 12 on all of them, here's 11 on all of this locus, here's 14 of all of this locus. So we can pretty much conclude to a near certainty that William, their distant ancestor up here, had that number of loci. Especially when we find some of these yellow numbers, these are what we're concluding about William, when we find many of those yellow numbers also in the other descendants on the other branches. So the squares that are colored blue are the squares that all agree with each other and agree with what we're imputing for William up here in the yellow row. And the squares that have been left white are ones where there's a disagreement. So for example, here's a 29 in a column that's otherwise consistently 28. Therefore, this is a mutation. Somewhere along the line that got to T4, there was a mutation in the short tandem repeat. This is probably easier if instead of writing the actual lengths of the repeats, which are not relevant, we here just show the differences from William. So the white squares are the same white squares as before, but now we show how much they differ. And in almost all cases, they differ by either +1 or -1. That is, there was either an event that added a repeat or an event that subtracted a repeat. So our goal is to model this and draw some conclusions about biology and also about some members of the Towne family. What might that mean? Well, we can see from the start that, for example, T2 just doesn't look like the others. He just has way more differences. So perhaps T2 is not actually a descendant of William Towne. That's going to be something that we consider later on. For now, let's do a biology problem. Let's ask if we can measure what the mutation rate is in this family. Now there's a step we have to do first. We have to learn how to unravel conditional dependencies. So let's work on that. Here's a little example, not the Towne family, but it will give you the idea. Suppose we have a set of events that are related causally the way they're shown by this tree. In other words, A happens, and then on the basis of A, B happens, and independently of B, E happens. Then on the basis of B, C happens, and D happens. Now what if we want to know the probability of this whole data tree, the probability of A and B and C and D and E? We can unravel this by conditional probabilities. Specifically, we can use the conditional law of probability to write the probability of A, B, C, D, E as the probability of E given A, B, C, D times the probability of A, B, C, D. Now, we look at this term, the probability of E, that's over here, given A, B, C, D. But we see that E has no causal connection to B, C, and D. So we can cross them out of the right-hand side. And this term is just the probability of E given A, which it depends on. Well, we continue in this same way. We can take this term over here, the probability of A, B, C, D, and we can try to make it as a probability of C conditioned on A, B, D times a probability of A, B, D. We look at C, and we see that it can depend on B all right, but it can't depend on D. That's off on another causal track. And if you think about it, it can't depend on A either, because once we condition it on B, that, in a sense, shields it from any influence of A. Any influence that A would have had is already seen in what happened at B. And so C doesn't depend on that. So this term, probability of C given A, B, and D, becomes just a probability of C given B. And I won't go through this one with you, but you unravel it in the same way. So this entire tree can be simplified to the product of this set of four conditional probabilities, but now they're quite simple. They're conditioned only on the thing directly above them, and then one probability, which is the original probability of A. There's an important idea lurking here, so let's make it explicit, and this is the idea of conditional independence. So for example, we can say that B and E are conditionally independent given A. Well, you can see in the picture what we're driving at there, but let's see it in the equations. What we mean by that is if we want to compute the probability of B and E given A, because we're going to do everything here given A, that's by the law of ANDing, I forget what it's called, or the law of conditional probabilities. That's the probability of B given E times the probability of E. I didn't say the given A in both cases. That just carries through on every term in the equation. Okay, so that's just a law of probability. Now we go back to the tree and we see the probability of B given E and A. Well, it doesn't depend on E. That's off on a different causal branch. So we cross that out. And now we get that the probability of BE given A is just the product of the conditional probabilities for B and the conditional probability for E. In other words, it's as if they're independent probabilities that we can just multiply together, but they only become independent once we tell the value of A, once we condition them on A. That's what conditionally independent means. Not everything is conditionally independent. So for example, B and D are not conditionally independent given A. Let's see why. The probability of BD given A is the probability of B given D and A times the probability of D given A. That's just laws of probability. But now there's nothing we can do with this. The probability of B given this, given A and D, there's no simplification of that because A and D are both on the causal line of B. You might say, well, D comes after B. How can it affect it? Well, it can affect it in the sense that if we knew what outcome there was at D, we would have learned something about B, and therefore it is causally related. Okay, so that's an example where things are conditionally independent, or an example where things are not conditionally independent. Let's go back to the Towne family and do the same kind of unraveling. What have I added to this picture? I've put numbers showing how many generations we have to go down. So you see the living Townes are 10, 9, or 11 generations descended from the original William Towne. And now let's figure out what the conditional independence tree has to look like. I'm going to make a simplifying assumption here. We're going to assume that there are no back mutations. That means we're going to assume that once there's a change by, say, 1 in the number of repeats, that change never gets undone by a later change. It actually could, in theory, get undone, but the reason that this is a very small effect on this data is we have 37 loci, and the changes are distributed across them, and it's actually rather unlikely that there would be much change more than a very small number, 0 or 1, back mutations in this data set. I'll leave it as an extra credit exercise if you want to work out the effect of back mutations. Well, why does that make things simple? If there are no back mutations, then whenever we see a 0 down at the bottom here, we can impute that along this line it must have been 0 all the way up to the top. It didn't change and then change back, you see. So here we have a 0, and this must have been 0. Well, basically it allows me to fill in the delta equals 0, that there were 0 mutations here, and the delta equals 0 here. Now, why does that help me in unraveling the dependencies? This is where we get to use binomial trials. Let's go from William Towne up here through Jacob down to Samuel Towne here. What's the probability that we still had 0 by the time we got here? It's a binomial probability. It's the probability of getting 0 changes in how many trials? Well, there are 37 loci, and there are 3 generations, and each locus and each generation was a chance to have a mutation. So if the mutation probability per locus per generation is something that we're going to call R, then the probability of having a delta equals 0 here is the binomial probability of drawing 0 things in 3 times 37 trials given probability R. Now let's go a little further down the line here to, his name seems to be Willard Oliver Towne, and he was born in 1779. What's the probability of this given the probability that we've already worked out above? Well, here we're going to go through, again, 1, 2, 3 generations and have 0 changes. So there's another binomial probability here. And you can work your way down in this same way. Let's pick one where there actually is a change. We come down this branch to T8 Towne, who has 1 change, and therefore the probability is the binomial probability of having 1 event out of 5 times 37. Do you see where 5 comes from? It's the number of generations. 1, 2, 3, 4, 5. Again, given this mutation probability R. Similarly, filling in here, 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 and here. Now you'll notice I crossed off some of the data. That's because here I'm interested in measuring the parameter R, the mutation rate per generation. And if the data is suspicious, if there's something else going on, like maybe the ancestry is wrong, then for now I'm going to delete that data. That's a little bit of a dicey procedure, and we're actually going to come back and learn some interesting statistics from that. But for now, let me delete this guy who had 23 changes, this guy who had 5, and this guy, T13 Towne, who had only 4 changes, but this is the one who only had 12 loci measured, so 4 out of 12 seems to be pretty large. Okay, so we're going to concentrate for a little bit on T8, T6, T3, T4, and T5. And now we're in a position, we've unraveled the conditional probabilities, and we've written down an expression, these binomial probabilities, for what we need to know. And we can now write down a statistical model for the data. What is a statistical model? A statistical model is just another way to say we have a way of computing, as Bayesians, the probability of the data given the parameters, right up here. Our model is not exact, but as we'll learn a lot in this course, statistical models are rarely, maybe never, exact. What are some of the approximations in our model? We've neglected back mutations, we've already mentioned that, and we're assuming that there's just a single probability R, a single number R that's constant across all generations and, more importantly, all loci. That's probably not perfectly good biology. It turns out that mutation rates vary across the genome, but for the purposes of our illustrative problem, let's stick with our approximate model here. And what is the model? The model is just the product of all those conditionally independent probabilities that we could write down, thus giving a probability of all the data. It's actually the probability of all the data except the data that we trimmed, but that's what we're looking for. And these are just functions of R. In other words, we could write down the binomial distribution and what these functions are and expand them out. So the probability of data given R is just some function of R. Now we get to do the Bayes thing. What we're interested in is the probability of R given the data. Bayes says that's the probability of data given R, our model, times a prior on the R. What shall we take for a prior? I'm going to take as a prior 1 over R. That's something that you haven't seen before. Looks a little strange. You know, usually we've been taking priors to be the uniform prior. Well, this prior is not the uniform prior, but it's called the log uniform prior. Why didn't I take the uniform prior? One good reason is that we think that the value of R here, which is a probability, is actually going to be pretty small. I threw out the notion that it might be something like 0.5%. The uniform prior gives equal chance to any probability between 0 and 1. So almost all of that probability is at pretty big values, like 10% or 30% or 50%. So if we want a probability that doesn't kind of emphasize the typical value of the range, like 0.5, we have to do something a little different. And 1 over R is called the log uniform prior because if you integrate it up over a order of magnitude, over a certain distance in the log, so for example, from a value R to a value 10R, that would be 1 order of magnitude, base 10. Well, here you do the integral, and the integral of this just comes out to be log 10, independent of R. So each order of magnitude, the one from 10 to 100, the one from 100 to 1,000, or more importantly for us, the one from 0.0001 to 0.001, will have a constant prior probability. So this is often taken as the non-informative prior when you don't even know the order of magnitude of a positive quantity and you want to give all orders of magnitude an equal chance in the prior. It's actually an improper prior because you can't do the integral from 0 to infinity of this. You get infinity here. And it's almost always okay to use improper priors in Bayes. It turns out it is possible to construct paradoxes with improper priors. One of these is called the marginalization paradox, so you can look that up on the web if you're interested in it. So here's the plot of the normalized of our answer, the probability of the parameter R given the data, and using that log uniform prior. And gosh, we've actually made a real measurement of it. It looks like the most probable value for the number of mutations per locus per generation is around somewhat less than 0.5%, right? 0.5% is here, so our measurement looks like it's about 0.3%. But because this is Bayes, we get a whole probability distribution. And we see that the value that I quoted, 0.5%, is a perfectly plausible value for this data. And the answer simply is, the answer based on our data, is this probability distribution. So this is real biology, almost, because we made some approximations. We've actually measured a mutation probability per locus per generation on the Y chromosome, short tandem repeats. This tells us something about how DNA actually replicates and how accurate that replication can or might be. So we spent a lot of time on conditional dependencies. You might wonder, did we really have to do all of that? What if I had just taken the binomials independently for each separate town? In other words, I didn't insert those intermediate nodes. I just counted how many generations they were down from William and used that binomial distribution for that number of generations times loci for the number of changes for each one, and just multiply those together as if they were independent, which they're not. I would have gotten the red curve here. So you can see that it does matter. The blue curve really is different from the red curve. The blue curve somewhat favors higher values of this mutation probability. But you also see that you wouldn't have been wildly wrong in this case to ignore the conditional dependencies. And if we had a very complicated model, it would be a whole lot easier to ignore the conditional dependencies. We'll come back to the Towne family for some fancier stuff later. In general, this idea of ignoring conditional dependencies and just multiplying the probabilities of the data as if they were independent, people actually do that. That's called naive Bayes. And it's just what the name says. It's naive because in real life, when you have a complicated data set, there really are dependencies, and an accurate model really would figure out how to disentangle them. But people often do naive Bayes. The reason is sometimes you just can't figure out how to disentangle the dependencies in the data. You just don't know enough about the experiment to know what they are. So it's mathematically incorrect, but it's sometimes all you can do, and it might be better than doing nothing. We didn't do that. We did real Bayes, unraveling the dependencies, but we did make one cheat. You'll recall we did delete 3 of the Towne's family from our model. What happens if we add back the 2 that maybe you might have thought I shouldn't have deleted? I'm not going to add back this guy who had just some huge number of mutations. I forget his number now. Was that T2? But I am going to include these 2, and that model will be the old model times 2 extra binomial terms. And that gives this result, the green result, which you see is really different. Well, it ought to be different because if these are really descendants of William Towne and they have these relatively high number of mutations, 5 and 4, then it would seem that the probability of mutations per generation simply has to be a lot larger. And you see it would raise the peak up to something like 0.6%. So which of these is right? That's the puzzle shown by this cartoon of how to trim data. We really shouldn't have trimmed the data. We really should have figured out a better way of doing it. And we're going to come back to the Towne family later on when we want to talk about how to do data trimming in a more principled way.